Hello everyone, this is Abdullah. Thank you for having me. I'm going to talk about the Malware Challenge. But before we start, I would really like to thank the organizers of this workshop who helped us set this challenge, and I would like to thank the MIT IBM Watson AI Lab for sponsoring the prizes. Since this workshop focuses on adversarial learning methods, UNMA and I have been thinking about setting up this challenge as a platform for our community towards thinking beyond adversarial attacks in computer vision applications, as well as pushing the state-of-the-art techniques in developing defenses and attacks for cybersecurity application. And in this line, we share similar goals with workshops that have been conducted in the past. For example, the AI cybersecurity workshop at AAAI 2019. So to this end, we set up a simple task for this challenge, mainly towards developing robust ML-based malware detectors. So let's say you have a bunch of files, portable executables, some of them are malicious, some of them are benign, and we are interested in developing a neural net model that is going to be classifying them. And so you would train this neural net by minimizing its loss and making mistakes of classifying PE files. So you might ask what kind of representation we could take these PE files to have. One possible representation would be to take one of the open source parsing tools, and for example, the leaf parser, that will peek into the executable file and look at kind of features. So for example, the list of imported functions or the API calls that the executable file makes. And so you could build a binary indicator vector that at each entry will tell you whether a specific API call is being made or not. Now, since malware authors are interested in having their malware files being or evading detection by the malware detector, they might think about changing these representation so that it will make it difficult for the detector to detect them. But then they also at the same time have a constraint of not really changing the kind of API calls that they are making, otherwise the PE file will not work anymore. And so the threat constraint that we consider in this challenge is that the malware authors are only allowed to add additional API calls. So for example, for this specific API call at this entry, it's not being used by the PE file, but the malware author could add it without changing its functionality so as to fool the detector. But for the API call at this entry, they cannot remove it because it's imported to the functionality. So you can think of these binary indicator vectors as vertices in the hypercube, and they could move to certain vertices by setting these bits, but some other vertices they are not allowed to move to. And so a robust malware detector should take into consideration all the possible vertices that a specific PE file can go to. And so with that, the standard setup of training a detector moves or translates from the natural training setup and minimizing the loss towards minimizing the worst possible loss that the model could have by changing the kind of features or changing the vertices of a specific PE file. So you could really view this from two sides. From the attacker point of view, they would think about what's the best way to build an adversarial version of the features of my PE file. And at the same time, from the defender point of view, they would think about what is the best way to build a robust model such that any kind of adversarial version or variant of a PE malicious file that could be presented to the neural net, and it will still classify it as malware. So in line with these views, we set two tracks for the challenge. In the attack track, the task is to generate adversarial versions of malicious PE files, such that they evade detection by an ML-based malware detector, and at the same time, they preserve the functionality of the malware at hand. And so one way of encoding that constraint is as follows, is that if you take the feature vector of the original PE file, and have it element-wise and with the feature vector of its adversarial counterpart, the outcome should be the original feature vector of the PE file. All right, so this is for the attack track. For the defense track, the task is to train an ML-based malware detector that's going to be robust to adversarial attacks, such as those generated in the first track. But then at the same time, it should have also a good balance between false positive and false negative. All right. So with these two tracks, let's go to the submissions. For the attack track, we had 5 submissions. And of course, in our tool and pipeline, we made sure that there is some sort of checks that will make sure that all the constraints are not violated and they should be satisfied. So for example, we had a problem with the submission by Raphael. The tool really raised an error about some of these files are violating the constraints. And so we had some communication with Raphael about fixing this issue, but we ran out of time. At the time of preparing these slides, we weren't still able to run the submission. So, but maybe in the future we'd be able to publish the results afterwards. But anyway, on the other hand, there were 4 submissions that ran smoothly with our evaluation tool, and you could see some of them are based on GAN, some of them based on ElasticNet, some of them are based on randomized gradient ascent. Okay, so this is for the attack track. I'm going to put the slides on the challenge website so that if people are interested in looking up the description or contacting the authors for these attacks. Now for the defense track, we had 6 submissions, and unfortunately one of the submissions did not really run on our evaluation tool. We found that this is mainly due to version incompatibility. We had communicated this issue to Koamai in this instance, and we ran out of time. We weren't able to get the model to work at the time of preparing these slides. But hopefully, in the future, we will fix this in the future with our author Koamai, and then we might get to publish the corresponding results. But on the other hand, the other submissions ran smoothly on the evaluation tool. And what's interesting is that some of these methods, although it came independently from different authors, they share the same kind of idea, which is the non-negative neural networks. So this is one. The other kind of submissions looked at generating an ensemble of models, and the way their decisions being aggregated is based on the attention mechanism. And also there are other methods that look at doing inner maximization in a different way, either choosing different maximizers or making some sort of a gradient ascent in a randomized greedy fashion. Okay, and I have put some pointers to the neural network, non-negative neural network, and the authors of the attentive mixture of experts have kindly shared their a document that describes their method. I'm going to share that on the challenge website. Okay, so these are the submissions. Let's look at the evaluation and how are we going to do it. For the attack track, the submissions were evaluated based on their evasion rates against the strongest model that we have, including those submitted to the defense track, meaning that we rank the submissions by their worst evasion rate, and so the winner would be the one that has the best worst evasion rate. I'm going to show this shortly. And now for the defense track, since different members of the security community have different desires with respect to the true positive and the false positive trade-offs, so we had 2 setups for this evaluation. One in which we evaluated the submissions based on their F1 score, against the strongest adversaries, including those submitted to the attack track. In other words, we rank these submissions based on their worst F1 score, and so the top is the one that has the best worst F1 score. Okay, so this is to just to make sure that we have a good balance on precision and recall. But then you might ask, or in a really security setup, we might really be interested in just making sure that we never misclassify malware files. And so in the second setup for the defense track, we evaluate submissions based on their false negative rate, or to put it differently, the evasion rate from the point of view of the attackers, of the strongest adversaries. In other words, we rank all of the submissions based on their worst false negative, and so the model with the best worst false negative is the winner. Okay, so I'm going to show what that means in the next slides. Okay, so let's go to the defense track result, mainly F1 scores. So here I'm showing the submitted defenses, and we're going to evaluate them against baseline attacks as well as the submitted attacks. And so if you see here, these are the F1 scores. So for example, this is the F1 score of this model in the natural setup, where we are not really perturbing the malware files, and so on. So what we see here, we identify what's the worst F1 score for all of the models. So for example, the natural model here has an F1 score of 0 in the case of the attack GAN with tips, and the rest goes on. But then what you identify, the model with the best worst F1 score is the model that was trained with the Grams method. It achieves 0.895 F1 score, while the rest of the model is 0, 0.5, 0.6, 88, and 0.79. There isn't really a big difference, but yeah, we're ranking them based on the F1 score. Now, so this is with respect to the defense track based on F1 score. Let's go to the attack track based on their evasion rates. So again, here we are evaluating these submitted attacks based on the models that we have. So here, what it means is that the attack submitted by the Grams on the natural model, 93% of the files get misclassified. And so for us to identify which attack is the best, we look at their worst evasion rate. So in this case, for example, Grams, the worst evasion rate is 2 against the NNN model. For AGA, the worst evasion rate, 0, doesn't really evade. The same case with GAN with tips. And for ENIA, the elastic net attack is 1.6. Okay, and so based on the worst evasion rates for these attacks, the Grams method is the winner. Okay, so far we have looked at the attack track based on evasion, defense track based on F1 score, and now we're also going to look at the defense track based on the evasion rate. So for us, we would like now to assess how robust these models against the evasion rates, against the attacks, and so we rank them based on their worst evasion rates. So for example, for this model, and the rest of the models, the worst evasion is 44, and the case of Grams is 9.7, 10.8, and rest goes on. And so the one that has the least worst evasion rate is the non-negative neural network model. And so that's the winner in this track / evasion rate. All right, and so in summary, we have 3 winners for the attack track. Evaluated based on the evasion rate, the Grams method seems to be the most effective one. And for the defend track, since we try to seek a balance between false positive and false negative, and we try also the setup where false negative is more sensitive, and we would like really to not misclassify any malware file. So the Grams method seems to be doing well with regard to F1 score, and with regard to the false negative, the non-negative neural network is coming first. And so with these insights really brings some future research questions. We saw that the non-negative neural net is really robust against evasion attacks. So for example, here you see both of these are based on the non-negative, and they really achieve fairly low evasion rates. So with respect to Grams here, well, even in the case of Grams, there is one, but still, it's a good in terms of the evasion rate as a training method. So the question, but then the way that they fail on their F1 score, because if you look at the true negative rate, they degrade with respect to the Grams. Okay, and so the question would be, can we improve the precision of non-negative neural network, or can we combine these methods, the non-negative with this randomized greedy gradient descent? That's all. Thank you very much. These are the certificates for the winners for the attack track and the defense track based on the evasion and based on the F1 score. Thank you very much. If you have any questions, you can please send me an email. And we're going to upload this on the challenge website.